All right, well, thank you for joining us here on this review for our meteorology final exam. Hopefully you have this exam review with this list of topics, and there's also a practice exam. So many of you have gotten that completed. Let's go through this list of topics. The journal entries. Please be able to recognize correlations between the weather data in our journals and the conditions outside. There are some good questions in that practice exam with sample journal entries, so hopefully you've looked at those. But first of all, just be able to recognize what those entries are. Our humidity, we've been labeling as a percentage of moisture. The precipitation is how many inches of rain we've been getting. The pressure, inches of mercury. Our dew points, that's temperature in Fahrenheit. Now remember, that's the temperature when moisture, vapor, condenses and will turn into liquid. Really, a cloud is just the temperature in our atmosphere. A cloud forms when the temperature in our atmosphere reaches the dew point at higher elevations. The temperature, that's in Fahrenheit, we've been writing down, and the wind speed. The thing with wind speed is it's a miles per hour, but we've also been writing the direction. And direction is, if you look here, the wind speed and direction, it's the direction it's from. So if we say there's a north wind, that's a wind from the north, moving south. Okay, so be familiar with those journals. The phase changes. You've been doing pretty good with that. That's kind of seems to show up a lot on some of our quizzes and our questions. But yes, solid to liquid is melting, liquid solid to freezing, liquid to gas, vaporizing. The opposite is condensing. Now, remember, melting and freezing are the same temperature. Just depends, is it getting hotter or is it getting colder? Vaporizing and condensing, same temperature. Just depends, is it getting hotter or getting colder? Now what's interesting though is you can evaporate water without having to boil it. It doesn't have to be 212 degrees outside for there to be moisture or vapor, I should say. So we'll look at that. That means the pressure affects the phase of the water as well. And then the weird ones, if you remember our dry ice, it's sublimes. And then the opposite of sublimation is deposition or depositing. And that's a hail. I mean, you think of water vapor dropping out of the sky, water vapor depositing, that's hail. So, yeah, okay. So be familiar with those phase changes. I would also like you to recognize specific properties of water, or special properties of water. So one of them that's weird is ice floats. We take that for granted, but that means water is less dense as a solid. It's very unique for most materials become more dense as they solidify. Water does stick together very well. I don't know if you remember trying to put drops of water on a penny. Water would stick to the penny a lot better than, say, some of the alcohols or some of the oils would, or some of the other solvents we had out. And water takes a long time to heat up. Also, conversely, it takes a long time for it to cool down. That's what we say there, is that water has a relatively high specific heat. And just think of the times even just boiling our cabbage juice last week, the water was the last thing to boil, the last thing to get hot. The glass got hot, the ceramic on top of the hot plate got hot, but the water was the last thing. It took a long time for that to heat up. Be able to look at a vertical profile of the temperature in our atmosphere and recognize what type of precipitation would be forming. So let's take a look at a couple of those here. So let's see. So that would be, so the vertical profile, so hopefully you've seen this picture before, but yes, it gets colder as we go up in the troposphere. There's our ozone layer within the stratosphere, but that's where it starts to get warmer again. And then up near space in the mesosphere, it gets colder again. And then up, really space, really it'd be pretty dark there. It starts getting warmer again. out in the thermosphere. So temperature increases, then it decreases, increases in the stratosphere, and then as we go up in the troposphere, which is where weather occurs, the temperature goes down. It goes down as you climb the mountain. So if we look at these vertical temperature profiles, now this is all where the moisture is. Now remember, moisture doesn't really pass through the tropopause. Water will freeze before it gets that high. So all the water stays around here on Earth. These vertical temperature profiles here go up to about 3,000 meters. That is well within our boundary of the troposphere. Snow just means that the entire time we're traveling up in the atmosphere, it is below 32 Fahrenheit, below freezing, below 0 Celsius. So if you look at some of these other vertical temperature profiles, rain just means that as that moisture falls, it's going to get to a spot where it does become above freezing. So then that ice crystal melts and falls to the ground. These little pictures help too. It's frozen. Now it's not frozen. Then we could look at snow. Snow is where it stays cold the entire time as it's falling. Freezing rain. It's cold, 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 melts, but then it stays melted, then boom, right as it hits the ground, it's frozen. So the way the temperature changes within our atmosphere has a lot to do with the type of precipitation that falls. The difference between sleet and snow, sleet will melt, but then it will refreeze before it hits the ground. Whereas freezing rain pretty much freezes right as it hits the ground. Sleet will freeze a little bit higher up in the atmosphere before it hits the ground. So please be familiar with those vertical temperature profiles and be able to compare rain, freezing rain, sleet, and snow. The layers and boundaries of our atmosphere. So the troposphere and stratosphere, those are the two I really want you to be aware of. Those are the two closest to the ground. And then that boundary between them, where water doesn't pass through, that boundary layer is called the tropopause. Our types of clouds. I do want you to be familiar with these pictures, so let's look at these. It's maybe been a little while. But these kind of wispy shaped clouds, these are cirrus clouds. These clouds that start to look white and fluffy, those are cumulus clouds. This kind of dull gray, you can see some of these dull grays, those are stratus clouds. And then the idea is if this cloud becomes dark and stormy, whether it's a stratus cloud can become dark, we call them nimbo. So you can have nimbostratus, you can have nimbocumulus, or we say cumulonimbus. And then the other prefix I want you to be familiar with is the alto prefix, which really just means the clouds are kind of hanging around at this middle level of the atmosphere. So our cirrus clouds, our stratus clouds, cumulus clouds, nimbo means dark or rainy, and alto means kind of mid-level of our atmosphere. Regions, let's look at this here. Regions within a cumulonimbus or thundercloud. So let's take a peek here at a big cumulonimbus cloud. I want you to recognize where the warm air is being pushed up, the cold air is being pushed down. It's that motion that kind of allows the cloud to organize, that contributes to the hail and the lightning that can occur with these type of clouds. The precipitation is going to be occurring where these cold downdrafts occur. We kind of say the positive charge gets uplifted there, the negative charges kind of get pushed down. It's that separation of static electricity that forms lightning. This is the anvil shape of the cloud here. If this did develop into a tornado, it would be out here in this piece, this front leading edge, if you will, because this cloud is moving. If you look at the wind here, it's moving. This anvil, just think of it as getting blown over that way. So this anvil is the direction it's moving in. This shelf cloud, this is where you would see a tornado form. And this back edge here, this is where all the rain would be. Now, as this is circulating, sometimes on a Doppler radar, you can see this overhead view of some of this circulation, and that's called a hook echo, and that is really the Doppler radar signature for a tornado. That would be a tornado on Doppler radar. That would be a tornado on Doppler radar, but it's also an overhead view of a pretty big cumulonimbus cloud. Okay. Tornadoes. The vortex is the center of the tornado. That's the region of lowest air pressure within the tornado. You can tell that the air is flowing into that region of low pressure. And that's kind of just a model for really our global weather. Is air will move from high pressure to low pressure. Same thing in the tornado. If you remember putting your finger down in those little vortexes that we made, this area here, there was no air, no water in this, but that is the region of low pressure. So low pressure is the center of the tornado. Air is flowing into those tornadoes, into that vortex. Adiabatic cooling, that just refers to the idea, it's really climbing the mountain. As air pressure decreases, as air starts to spread out, it generally gets cooler. So as you climb the mountain, part of the reason it gets colder is because that air is spreading out. An F0 tornado is really not much of a tornado. An F5, or sometimes you might hear EF5, those are the most damaging tornadoes. And then, like I said, just be able to recognize that Doppler radar signature, that hook echo of a tornado. All right, wind patterns. I would like for you to be familiar with the wind patterns that we see around our globe. Let's kind of start there. So remember, around our equator is not much wind. The doldrums, that's the International Tropical Convergence Zone. And really, the convergence means these northeast trade winds and these southeast trade winds kind of cancel out. So that's why this is a calm region here. The trade winds kind of got their name because ships and boats that were interested in trading around the world would use these winds to push their boats across our globe. The horse latitudes, another place where you could think of it, the prevailing wind patterns cancel out. So these horse latitudes, not much wind there. Now we live here, St. Louis. This is the prevailing southwesterlies. So on average, our wind is kind of coming up. I know a lot of people say it's coming up from Oklahoma, coming up the Interstate 44 corridor. It's a lot of our weather. I know our principals are closely monitoring the weather for graduation this weekend, and they're really looking at what kind of storm systems are moving in. And the first place they're really looking at is those prevailing southwesterlies. So kind of be familiar and be able to look at this map and just answer questions about wind direction and recognize that it's calm winds in the horse latitudes, calm winds in the doldrums. All right, now once again, the wind direction is just the way we list that or label that is we say where the wind is coming from. So a prevailing southwesterly is wind from the southwest part of our state, from Oklahoma, etc. And the relationship to pressure, we'll look at that here as we come back with the Coriolis effect. But the way the wind spirals around has a lot to do with the air pressure in that environment. So these fronts, let me show you the picture I want you to be able to interpret there. With fronts, it's really just kind of looking at this picture and understanding what it's asking you. But if I said a warm front is approaching, so if a warm front is moving in, we would first see cirrus clouds. Now, depending on the moisture levels and the humidity, really, the cirrus clouds could start to collect and get darker and turn into cirrostratus. They could start to sink down a little bit as the warm front approaches and turn into altostratus. And then if it really wanted to start raining and get really dark, those nimbostratus clouds would start appearing, and they're a little bit lower to the ground. So the pattern of clouds for an approaching warm front would be cirrus, cirrostratus, altostratus, and nimbostratus. Now, if a cold front is approaching, so the warm air is leaving, and this cold front starts to push in on us, well, that's when it's boom! Just all of a sudden we see a pretty, all of a sudden it just kind of gets dark really quick. These big storm systems move in real quick. So that's an approaching cold front. It's the approaching warm front when it's kind of gray all day, kind of starts to drizzle, starts to rain more steadily. So it's not a memorizing thing, but look at this picture and recognize that when a cold front comes in, boom, cumulonimbus. As a warm front approaches, cirrus, cirrostratus, altostratus, nimbostratus. All right, now let's look at the jet stream. It's another thing another picture I want you to be familiar with. The jet streams are really just kind of like on a normal jet stream, we kind of say, this is also that prevailing southwesterly winds that we get across St. Louis. But if you look at the globe here, here's kind of a picture of the jet stream, and that's just really the motion of the air up in our atmosphere, and kind of in general how this air kind of circulates around with us. Now, the ocean, the temperature of the ocean, and it comes really back to those special properties of water, do contribute to this a lot, but where these warm ocean currents occur does affect our jet stream. All right, and that effect is really oftentimes referred to as El Nino. So when we have this warm ocean water kind of migrating a little bit off the equator, getting a little closer down here to Mexico, a little closer to North America, we will typically see these two patterns in our jet stream. So the thing I want you to recognize is, this is currently 2015 is an El Nino year. Our typical jet stream pattern looks like this. All right, and you can see, in general, our spring arguably has been very kind of stormy, a lot of wet weather coming up this way, and this has kind of been our pattern for this El Nino year. So the El Nino, a simple way to look at it is there's two patterns on the jet stream, two arrows. A non-El Nino year, the jet stream would look like that. Okay. Now, the Coriolis effect refers to the spiraling of the air. So even if you kind of look at, say I just looked at a weather map here, and you can even make out this kind of, well, look at that. This kind of looks like this wind here. You can see how here in the Midwest, here in the western part of our state, we get this spiraling wind pattern here. Well, it's going, what is that? That is counterclockwise. So I am guessing that counterclockwise is actually rising air in the northern hemisphere. So this would be, if I were to look at this is the wind map, but now if I were to look at the same image, and yes, right here is this low pressure. This low pressure is where I would see counterclockwise spiraling. The high pressures, remember, that's what pushes that's what pushes water down the drain. So we kind of did some funnels and let the water spiral down our drain due to the air pressure pushing it. High pressure is sinking air. High pressure pushes air down the drain, pushes water down the drain. High pressures in the northern hemisphere spiral clockwise. So that's what that Coriolis effect refers to, and really we see just the opposite in the southern hemisphere. So please kind of be familiar with the Coriolis effect and be able to predict the motion air will spiral based on if it's a high or low pressure system. High pressure is sinking air. Low pressure is rising air. If it's sinking air, here in St. Louis, northern hemisphere, clockwise. And that does contribute to these weather patterns, and really a lot of these kind of moisture patterns and Doppler radar, we see that Coriolis effect occurring as we kind of track the motion of our air around. But now remember, the air for the most part, orbits with the globe. So, as our world is rotating in 24 hours here, in a full day, we don't experience a full world's worth of weather in one day. For the most part, the air pretty much stays with your region within a day. So we don't go through all the Earth's biomes in one day. And that's part of what contributes to the Coriolis effect, is because around our equator, the air has to move farther. So that's why it's really moving faster as it orbits, or as it circulates, rotates with the Earth. And that's part of what contributes to that Coriolis effect too. It's very complicated. And with Coriolis, just please, the easy thing to remember is water spirals clockwise down the drain in the northern hemisphere. And then from there you can make all the other associations with the spiraling. All right, the biomes. This is a little more recent, but tundra, I think you can kind of remember where those are. A lot of that is, if you remember, we colored that biome map. And so I just want you to be able to look at that biome map again and kind of match up where these regions are. But you'll be given the key and of the map. But tundra is kind of like frozen desert. It's a fair way to think of it. Taiga, fair way to think of that. It's kind of a colder evergreen, more of a pine forest a lot of times. Grassland, it's really, you could think St. Louis, Illinois, we're right in the middle of the grassland regions. We're also kind of right in the deciduous forest biomes. Deciduous just meaning the trees will lose their leaves in the winter. Tropical forest really just means the trees stay, the leaves stay all year, and those are in the tropical regions. The desert, everyone knows what a desert is. And then ocean is also considered a biome. And arguably, that is the world's largest biome and has a lot to do with the world's climate, just in terms of what the temperature of the ocean is. So some things that kind of contribute to the world's climate is, the gases in our atmosphere, the radiation coming down through our atmosphere. So also kind of more recently, you looked at that electromagnetic spectrum and kind of the idea that the sun, and really the stars in space, really give off this whole spectrum of light, this whole spectrum of energy. A lot of those pieces of radiation or types of radiation are absorbed by our thermosphere, our mesosphere. The ozone in the stratosphere absorbs an awful lot. If you see a lot of these kind of types of radiation stop in our stratosphere, and that's because of the ozone. And that's really what it's doing, is blocking or absorbing a lot of that radiation. Now, obviously we do need some radiation, and it's a good thing. A lot of it gets to our Earth. It's the energy for all of our plants. But then it's also the idea that the temperature we experience here on Earth is really a function of the radiation that hits the ground re-radiating back up. And we see most of that radiation re-radiating back up as infrared. All right, so infrared is the result of the Earth's surface absorbing sunlight. And that's really what contributes to our temperatures here on Earth. All right, here in the troposphere. So it's the idea that as all of this energy comes back down and gets pushed back up through our atmosphere, all this energy re-radiating back up is infrared. Now, then some of the molecules in our atmosphere absorb that infrared. And a big one was carbon dioxide. And so that's a lot of what has to do with our temperature here on Earth, and it's really, there's a direct correlation between the amount of carbon dioxide in our atmosphere and the temperature. And even we can go back millions of years. I don't know, we looked at some ice core data, and that was able to kind of correlate with global temperatures over the past million years. And even the more recent ice core data was able to correlate with our CO2 levels that we can directly monitor and directly measure today. And then acid rain, that's really kind of what we've been playing with here these last couple days, was kind of looking at how we monitor acid rain, or the pH of our environment. So hopefully you kind of got those worksheets where we've been kind of playing with these cabbage juices. But you know, the whole purpose of that is it's really the color, the leaves, the plants do tell you about the health of the atmosphere, and all those indicators that we use to kind of monitor pH are just fruit juices and just plant juices, and they change color with the pH. And so I want you to recognize, let me think here, pH, about normal rain's about a 5.5. So normal rain, healthy rain, is a little acidic. Because remember, below 7, below a pH of 7 is considered acid. So normal rain is normally a little acidic. A lot of plants thrive in a slightly acidic soil. Now in St. Louis, we're a little more acidic than 5.5. We're about 4.5 is the average pH of the rain here in St. Louis. But even still here in St. Louis, even though we might have acid rain, I think, you know, our soil, I think, is pretty healthy, even though we do have this kind of, right here, this 4.5 as a pH. There are some regions which have even more acidic rain than we do, and even in the Midwest. But yeah, what's causing this acid rain? It's really the molecules, the particles in our atmosphere. So the few I want you to kind of recognize or be familiar with for acid rain: nitric acid, which is really just coming from the exhaust. So nitric acid is from car exhaust mixing with moisture. Sulfuric acid is a lot of burning of fuels, burning of coal on an industrial level. And when that sulfur and the coal gets in the atmosphere, sulfuric acid can form. And even carbon dioxide. What was funny, I just left these out from our last class. And these were all, you guys made them all turn green. But really, as they've been sitting out, they changed color just sitting in our room overnight because of the carbon dioxide. So carbon dioxide can settle into moisture and mix up with moisture and form carbonic acid. And that can also kind of contribute to the acid rain. All right, now, some of those same molecules can accelerate or catalyze the depletion of our ozone layer. So a few of the ozone depleting catalysts, well, what's interesting is water can be one. Even though water doesn't naturally reach the ozone, water from jet fuel can accelerate that ozone depletion. But remember, ozone naturally depletes anyway, so it's kind of always trying to find a balance. But methane can also accelerate that depletion of the ozone. And then really the car exhaust can also make acid rain, but it also can contribute to ozone depletion. So, and then the final one is some fluorine or chlorine can also kind of contribute or accelerate or catalyze that depletion of the ozone. If you have questions, but hopefully you've kind of read through this review. Now, really what I would encourage you to do, and what we'll kind of talk you through in class more our last couple days, is this practice final, but it will be very, very similar to your real one. So thanks for your attention, and good luck, and please keep asking me questions, and I look forward to working with you during our last few classes together.